So, okay, today we will talk about Markov chains, and I think next week as well we'll talk about Markov chains again. And to be honest, this is one of my really favorite topics and amazing concepts. And I think it's very open into. I mean, you can find its effects in many fields. Let's say from natural language processing, and of course in probability theory, and then in control system, and then in dynamical systems, and it's everywhere, and it's very simple at the same time. But this is a very like self-organizing map, which is in principle simple. It has a lot of functionalities. And there have been a lot of works on Markov chains, and Markov chains, unlike self-organizing maps, is a bit old. This method was introduced in 1906, where at that time there were no computation and no data in principle, no big data or enough data, and this was a contribution of these famous mathematicians. Andrei Markov, he has a lot of contribution as well in principle in probability theory and mathematics. And his original work was on the modeling of stochastic systems, where one is interested to study the sequence of random events and their underlying state space. And his famous application is working on a poem, and I think I read some of his a translation of his original paper, that he tries to convince, as you will see later, that you can capture the complexity of this dynamism of like characters. Think about the characters in a language, the way people are writing in a text, for example. He was trying to find a way that only through this observation, sequential data, you can encapsulate these probabilistic patterns between characters. Imagine, for example, when you say hello, you just say H, then it's E, and then L, L, O, right? So if you have, like, let's say all the letters are your characters or your states, then you can count. For example, if you have a lot of books, you can open and just start from the first line, say, okay, the first word is hello, okay, H, and H is the state, for example, 1. And then next state is, for example, you find E. Then you say after H, it comes E, and then you say again E, again L, L, O, and so on. And he just says that, think about it like a continuous sequence, which has a meaning for itself, but we don't want to start with the rules. And this was very hard to be accepted in that time, and I think he didn't manage to convince people, especially in linguistic, that you can make a model of that. And the problem was that you didn't have enough data, and you didn't have a lot of computational power, imagine. And this will be the topic that we will discuss next week. And I think for me, this is the basics of the so-called neuroprobabilistic language models, which nowadays works in deep learning, and then this famous application of word2vec. They are all based on that. But today I will just mainly focus on dynamical systems, which is more the area which has been more studied, like in terms of Markov chain. And so, in principle, I just want to summarize the introduction, is that you can think about Markov chain from the point of view of dynamical systems, which I will talk today, and I will show you two real world applications that I did before. And then you can think about it from the point of view of representation. This is the main problem again in principle machine learning, how to represent objects. And he, I think, proposes for the first time a very nice way of data-driven representation, but this will be the next session. And then I will show you the properties and applications of this simple concept of Markov chain. And I think you will see that at the end you don't need something more than addition and division. You just sum numbers and then divide, and then you just keep this matrix, and it works perfectly in many applications. And then I will talk about limits of this Markov chain. So if we want to start with Markov chain, I would like to start with the idea of random walks. This is a more, I would say, classical way of approaching Markov chain. And then you have the notion of Markov property. Just imagine that you have this idea of random walker, that this random walker can decide to go one step backward or forward or left or right. So in this case we have a discrete choice, which is either -1 or +1, and this random walker starts from 0. And then our observations is that we only look at 10 steps. So in principle, the maximum minimum here is limited, right? Because if you start at the state 0, if you're all 1, 1, 1, 1, 1, in 10 steps you're just 10. If you're all negative, you're minus 10. So you're in between. But now I'm going to visualize this. I'm to render this for several random walkers. It always starts from this state and then goes somewhere. This means that takes this, for example, let's call it right, and then it goes left, left, right. You see that this is a kind of decision, but it's pure random. It's based on 50-50% choice. And every time that you run it, it's a different pattern. And if you increase the size of observations, your state space is exploding. Because now if I have 10,000 steps, it's possible that I go to 10,000 to minus 10,000. So you have more sparse space now. For example, this is another step. And every time that you run it, it's like random, right? And here you don't care if there is a logic behind or not. You just assume that's random. So if for this case, for example, if I just want to know the unique states, it says it's a very specific case. Let's do it again. Here it says that what I define as a state is the number that you reach, for example, right? So it says the unique states that I reach with this random walk is, of course, 0, minus 1, minus 2, minus 3, and minus 4. So if you run it again, it will go to different states. And think about it like a tree. And for example, you have this in many games, like you have it in chess, you have it in AlphaGo, or this kind of Go game, not AlphaGo, sorry. AlphaGo was the solver. The Go game, or any game that you assume, or even if you want to walk from here to that corner, then you have steps, and then each location of this room becomes your state. So this is the definition of state space, and then your choice are these random walks. So what is interesting here is that here, because of this choice of random walks, this is the formal way to represent this. If you want to know what is the state at time t plus 1, for that you don't need to know what was the state at all the previous time except the last time. Because imagine if you want to go to like 10, you either have been 11 or 9, right? And it doesn't matter if you have been in 5 or not in 10 steps before. So in principle, if you think about it as a kind of conditional probability, the probability of knowing the state is n, for example, or xn, or x and time steps n, depending on conditioning on the previous states from 0 to n, it's just equal to a state at time n conditioned to previous steps. And this is a very famous property. It's called memoryless processes, or Markov property, that you just look at your close neighborhood and then think about it. If you have a picture, for example, then you have a two-dimensional space, and then most likely you assume that the value of the pixel is related to the close neighbors, because if you have some kind of homogeneity there as well, you can assume this kind of Markov property. So this is a very generic property, and by that it's amazing, because by that I can make a simple matrix now that I have all the cells, and then each row and the columns are the same, and what I need to capture is to just know the transition probabilities from each state to another state. So if it was not the case, I needed to store all of these sequences all together. And this is the trick. You capture all of the sequences in a way, what you just need is the transitions from any state to another state. So then in principle you create a matrix which is called a transition matrix, and this matrix has n row is a n by n, is a square matrix. N is the number of states, and then you have the columns and the rows are the same. And if you, for example, if you have row stochastic, means that you say, if I count all of my sequential data, if I have, for example, 10 states, I just say from state 0, what was the chance that I go to state 0? From state 0, and in this case, for example, what was the chance that if I, in this random walker, what is the chance if I am at number 10, next step I'm at number 10? This is 0, right? Because you need to take a position either left or right. So in principle, this cell becomes 0. And then you just say from state 0 to 1 to n, right? You have all the states. So So you just make these relationalities. And what you need, I told you, is just summing and division, is that you just need to count. When you are building this Markov chain, you just, this transition matrix, you just need to count. Just clear which kind of states you have, and then when you're reading your sequences, you just say, okay, I was at state 10, now next step is 6. So you just add one, and then at the end you just divide each row by the sum of each row. Then it becomes a kind of probability, right? So this simple idea will show you that it captures a lot of interesting properties of these underlying systems. So in the classical case of characters in a language, for example, let's say we have, I don't know, 60 characters in the language of English, like including like all of these signs. So you have a matrix of 60 by 60, and if you just really care about one step ahead, one step before, you just have a matrix of 60 by 60, and then you can read as much as possible text, and every time you just look at the character, you just say, okay, hello, H, then E, then you go to a row of H, and then E, right? It's clear. So then we have this notion of row or column stochastic, which means that the sum of rows or columns are equal to 1, sorry. And then all the elements are non-negative, which means that it can be negative, right? They're either 0 or positive, and this fits, if you remember, with this Kolmogorov axioms to being a probability value. And then you can represent this matrix as a graph as well, right? As a directed graph and with some loop. So a very basic example is that, think about this very simple example. We have two states, either rain or sunny, and when we say if it's rainy, most likely, which means 90% tomorrow will be rainy, and 10% tomorrow, sorry, if it's sunny, I think it should be sunny, it doesn't make sense, or yeah, it's arbitrary. Let's say rain. If it's rainy, tomorrow will be rainy 90%. If it's sunny, it will be sunny 60%, and if it's rainy, it will be 10% sunny, right? So you can represent this with this simple matrix. You can read it like this, and now this is row stochastic, means that the sum of the rows are 1. So if you're here, you either go to this state or this state. There is no other options, right? But then it's sunny, 90% is sunny. It's sunny, and tomorrow rainy is 10%. So you can calculate, for example, this is a classical way of probability theory. You just say, okay, I'm sunny today, for example, today is sunny. What are the chances that in 2 days it's sunny? So you just need to count all the combinations, and then say, okay, today is sunny, tomorrow, one option that in 2 days it's sunny is that tomorrow is either sunny or rainy, right? So in principle you have two paths in this Markov chain. So you just need to calculate, for example, all the paths and then just sum them together. This is the way it works, but definitely it's not a good model for weather forecast, we know that, and I will show you later that this is not the main role of Markov chain. So the way we can do it is that let's just think about it, that when we say today is sunny, then you have a state vector which is 1, 0, because you can represent it like that, right? Today is sunny, tomorrow, and it's not rainy, so it's 1, 0. If you multiply this vector of 1, 0 and 1 to this matrix, actually you're doing this calculation, right? Because when you do this calculation, it's maybe I need to write it down if it's not understandable. You just multiply 1 by, no, it's 0 and 1, I think we start. 0 and 1. So you just multiply, can I move? Or sorry. Okay, it's not working. It's okay. So you have this matrix of 90, 60, and 1 and 4. So this is your state, 0 and 1. You just multiply this by this. 0 multiplied by 9 is 0, and then 64%, 60, and the second you do the same, you go to the next step, right? And if you remember, this is dot product, right? We did the same. for a lot of calculation. And the interesting feature of this nice Markov chain, not all of them, is that if you do it sequentially and over time, oops, not like this, it will converge. And this is very interesting property of these specific Markov chains, which are stochastic, that regardless of your initial state, the steady state is always the same. So, for example, think about that this could be a flow of people in this building, and then you just start counting how people move from this room to another room, from that room to another room, and then your states are, in principle, these rooms, and then you just want to know by average how many number of people are in this each room, because you cannot, and this is very fits with statistical mechanics in equilibrium, and it studies this kind of limiting distributions. It says that if you have this phenomena and then you just watch it for a long time, what if you take a photo in that time, after a long time, if you take a photo and then count number of people, this will be, for example, the number of people. Or if you count a lot of days and then simply just average over them, this will be the number of days that you will be sunny or rainy, for example. So this can be used as a data-driven input to your design, for example. If you want to design about, I don't know, for example, layout or any systems, this can help you a lot. But this is the very early things, very basic thing. So you can represent this like this. So you have two states, sunny day, rainy day, and then you have 90% will be sunny again. So you have this notion of loop, and then 10% will be rainy. And if you're rainy, it will be rainy again for 40%, and 60% goes to sunny. So it's very simple, but it's very powerful, and I will show you. You can do it in many applications. These are very basic applications. So now there are two interesting ways to look at this Markov chain. One is if you look at these cell values, you can think about it as a kind of network that it's representing this kind of conditional probability. So you can start like this game, that what if it's today is sunny, what happens in 10 days. You can just simulate it simply and then see a sequence. So think about this like if you want to predict next character, or if you want to predict the next move, or if you want to predict the next step of like next day weather. This is like a kind of probabilistic sequence generation. And then the other way would be if you have other systems that, for example, now you don't care about a specific day, but then you have some kind of continuous setup. For example, think about you have flow of particles of water molecules, and then you can make a probabilistic rule that how they would move. Like if the water molecule is here, next step, because of a lot of factors, would be there, and so on. So in principle, in those cases, for example, in this case of flow, you don't care about one specific water molecules, but what you care is about the overall flow. And then, for example, this is the case in traffic, for example. This is the case for example, this example of layout, for example. You don't care about the movement of one person. You care about the overall flow. You want to have a kind of representation of the overall flow. In that case, you can think about this Markov chain as a linear system. So it's a linear dynamical system. And then you can think about these values as the rates of these equations. And then, for example, you can say state at xi at a state of at time t is calculated like this, simply. This is just multiplication. So it might be a bit confusing now, but I just wanted to show you that you can think about it. If you think about it at the micro level, for example, if you have a mobile application that you want to predict how people move, this will give you a kind of probabilistic model of people. But if you think about it at the macro level, for example, you want to know if people migrate from this country to another country, right? For example, 10% stays in the same country, 90% migrates. And then from the other countries are doing the same thing. You just wanted to know by average after 10 years what is the population of each of these countries. This is the macro level, and this is most of the time very important questions. There you can think about Markov chain as a kind of deterministic model. Right? And a common mistake is to use Markov chains for predicting specific sequences, because what we have, just think about it as a kind of time series prediction. We will see this in recurrent neural networks later. Just think about it that you want to predict the next move, like a language or any time series, for example, or sequential data. In Markov chain, what we know for one specific particle or unit is just what was the previous state. And in terms of time series forecasting, this means that you have a time lag of 1, which is in principle not a good idea. You should have different things. Like in recurrent neural networks, we have the notion of memory and this kind of long-term memories and so on. So this is Markov chain is not a good thing for prediction, definitely. But I've seen that this kind of confusion, and then they're comparing whether the result is good or not. It's not the case. So then there are a lot of small things that you should know, but we will fix it for today. Is that, for example, what happens if the transition matrix is changing over time? So because we assume that the system is linear, and because of that, these rates of these linear systems are fixed, and because of that you call it linear system. But if you have a nonlinear system, which means that the local rules are changing, so these rates are changing, correspondingly the Markov chains transitions every time is changing. So you have the notion of time homogeneous or inhomogeneous Markov chains, transition matrix or Markov chain. And then another thing is that when you have finite states or continuous states, like in this case of random walks that I showed you, if I just say it should be 10 steps, but if I say 100, 1000, and if I don't limit the number of time steps, it can go everywhere, right? So the state space is expanding, and in this case it's discrete. But imagine I would say that these random walks could be any number between -1 to +1, so it was continuous. So state space is exploding, and this is a very known problem for Markov chains, so you need to deal with it. And this is very similar to this curse of dimensionality that we talked before. So if I say 1000, definitely you have a larger range of values, right? So, but most of the cases it's easy to convert them to finite state and time homogeneous transition matrix, and then discrete time. Another thing is that again we idealize these systems because we assume that there is one simple clock, like for all of the particles. But then sometimes these partitions, this transition might happen in different speeds, right? So then in principle you don't have this notion of discrete time. So maybe this transition would be in a continuous time, and over time this transition matrix itself is changing. So if you relax these assumptions, there are not many works on that. Even in I think mathematics as well, there are few people working on this, but it's in principle useless. And I think then it becomes very similar to what is called nowadays as non-equilibrium statistical physics. And what we usually know here is we study these systems of dynamical systems when we assume what is their limiting distribution or when they are in the steady state. So still there are a lot of things to do, but nobody knows what to do. At least I don't know. So nevertheless, the beauty of this Markov chain is that it's super easy to be constructed from the data. For example, if you know a lot of rules, like for water flow, if you know the equations, how particles are pushing each other, or you know the Newtonian equations, that gravitational rules and so on, you can build a linear system or even nonlinear system if you know the rules. But the beautiful thing with Markov chain is that if you have data of these observations, you can build the underlying systems in a data-driven way, in a very simple way, and if you add more data, it gets better. So for example, if I will show you in maybe 10 minutes, if I have a lot of observations from the real drivers in a city, that they're really driving, I don't know what are the rules of transitions if my states are located in the city. But with this Markov chain, you can encapsulate them. So in principle, any of these drivers could have different rules. So this is the case that you cannot write it down. And then in principle, you cannot simulate it. If you want to simulate based on some equations, you need to know the rules. But for example, there are a lot of applications, especially in social systems and cities, for example, that you don't know these rules. So your rules are usually arbitrary, and then you simulate based on these arbitrary rules, and then it works. But now with this data and big data, in principle, we can construct this Markov chain, and that's a beautiful thing. Now, then in principle, Markov chain, you can read it like that it encapsulates the rules, but doesn't know the rules as well. So if you want to say, okay, tell me what's the equations of these transitions, you don't know exactly, but it's completely data driven, because then states are arbitrary, you define it and so on. So it's just fit to the data. It's very similar to the other things that we talk in machine learning. It's not representational any longer. Whereas representational means that you need to know, for example, what is this context. You just say, this is the flow of water. So I need to know how particles of, I don't know, molecules in water or particles of air are moving. So you need to know the context. If it's about energy, you need to know how these energy transformers or energy distribution systems in a grid are working. If it's about economy, you need to know how these agents are acting. But with this data, Markov says, just give it to me in a kind of sequential data. I can construct these dynamics. Of course, it's not that detailed in a macro level. You cannot use it for predicting for one specific line, but it works for all of them. So as I told you, making this Markov chain is building this Markov chain from data is very simple. You just need a sequential data, and then you need to define your states. In this case, we assume that our data is capturing the information of these observations of these random walks every time, for example, for 10 steps. And then I say, let's say, for example, we have 10,000 random walkers. So I just say, what are the unique states that we have observed, or what is, for example, minimum, maximum. And then every time I just say, start with the first data, and then tell me what is the current value, for example, or the previous value. I think this start from 1. So we start from the first point of the observations, and then what is the next one, and then you have this matrix which is n by n. You just say, what should I do? Okay. Okay. So you just need to count how many times you have this transition from I to J. And then when you do it, and after that you do normalizations per row, and then you are done. And I will show you a few applications, but you can't imagine that that's it. And for example, Google PageRank algorithm works like that as well. Like this was the introduction of Google search engine in back 1998. They assumed a random walker on this network of web. So you have the connectivity, and then they assume that based on the number of links, you calculate the probability, and then simply you make this matrix, and then there will be some tricks to make it stochastic and so on, and it's called Google matrix now. If you search it in Google, for example, what is Google matrix? Yeah, it's called Google matrix. It's a jargon, right? It's not that different. It's a Markov chain, and I would say this is the first successful application of Markov chain that works really. And then, as you will see, the steady state values are the results of ranking of the pages, which is called PageRank. So let's remove this part. So back to the random walk example. Now imagine that we have 5 observations, for example, and then I think we start from states which is a random value. Let's delete this part. So I have these arrays or lists to just capture them. So I just say number of times step 3, for example, in this case, and then I say for the number of observations, each observation needs to watch 3 steps. So I start with the states random, and then every time I have defined this walk, which is either -1 or +1, and I just count the states, right? And then I just say capture all the sequences and so on. So then I just calculate what was the maximum and minimum values to define my range of states, and some of them have not been observed, for example. So if I do it now for 5, I get something like this. The minimum states in all of these 5 observations was -5 and +3, and then this is one sequence: 3, 2, 1, 0, 4, 5, 6, 5, 8, 5, right? And then think about this, that these numbers are not necessarily like a number, right? This can be state, these are like symbols. This can be the characters, this can be even clusters. You remember we did this clustering. Now imagine you have a high dimensional data. Do a clustering on top of that, and then you have like 10 clusters. So in principle, if you say, I want to know the transition between these 10 clusters, this is a kind of coarse graining, right? Or even you can say any data point is a state.
Yeah, positions in space,
anything.
tonality of pixels,
exactly.
whatever.
So this is that generic. It can be anything. And even it can be high dimensional vectors that are symbolized here. So we just make this, and out of that I make this simple matrix, which is not showing in a nice way. Yeah, you will see it in a better way. So now if I increase the number of observations, and let's see what happens. Now I have 10 times steps, 1,500 observations, right? So again, if I, like the case of rain or sunny, now I just draw a line for each state. But then here the states are, the probability of being in that state is the weight, like this case, remember? Even if you start with discrete values, after a while it becomes continuous, right? This is a ratio, it's not the exact value. It's a proportion of the values in that state. So now we have a lot of random walkers, and we want to observe the dynamics of these states. This is the question, not the random walkers, right? So if I visualize it like this, you see that there are a lot of them are fluctuating, and then there are some of them are kind of absorbing states. If you go there, there is no way back. And this is a thing for those cases that they go up, and then they don't change. So this is one way to look at it. The other one, which is interesting, and this is the idea of limiting distribution or steady state, is that if you start in the beginning, it's very volatile, right? Over time, they get converged. And if I just increase this to, let's say, to 200, it will be like that. So this is the case of a stochastic Markov chain, that when you have this row is stochastic or column is stochastic, there are a theorem for that is proved that they get stable. But there are a lot of other Markov chains that they are fluctuating over time and they never reach to a steady state. Even here, I would say, if you look at these values, look, for example, this is getting very stable, but these guys are fluctuating. So these are like local loops in your data that they are going back and forth. So they get trapped there, and because of that they never finish. Every time steps is like either this one or the other one. But over time, what is interesting is that Markov chain is the first eigenvector of the Markov chain, or that transition matrix without this calculation, is calculating the steady state distribution of your data. Now what does that mean? Let's make it like this. Let's say 30. So it still is not converged. What I do is that now I go and take a snapshot like this, and then the beautiful thing is that in each column, if it's a column here, in each column the sum is 1, because this is the proportion of each state, how much people or how much material they have in their own. And this is the meaning of limiting distribution. If I visualize it now for you, this is after, like, I select like every 4 steps, for example, or something like that. This is the initial state. I start with random states, and then quickly, because of this transition matrix, they get stable. And you see gradually, this is the final distribution, and this is like what you have here, like 2 of these guys. Now states are on this row. This is not the same as this one. Here we don't have time. This is timeless. But it tells you, if you have such a system, whatever is the system, over time, this is the chance of each state, that how many people, for example, are this room. For example, if you have 40 rooms, and then you let people do these random walks between this room, or even it's not necessarily always random walk, they have their own purposes, but you don't care, and that's the beautiful thing. It tells you over time, if you take pictures after a long time, you will see that the chances that how many people or proportion of people in each room is based on this distribution, right? So then you can take this eigenvector or the limiting distribution of the Markov chain as your input, for example, for your data. This is one factor, and then as well there are other methods like Markov chain Monte Carlo methods that for predicting. Like you remember these kernel density estimations that we had these very strange patterns, and then we were trying to fit parametric setups, parametric distribution to the data. You can use some kind of Markov chain that their limiting distribution is the desired limiting distribution. So it's a kind of sampling method as well. But yeah, you can read about it later. It becomes a bit complicated. So what happens here is this Frobenius theorem that if you have these nice matrices that they should be row stochastic or column stochastic and irreducible, which means that in principle there is a path from any point to all the other points, right? Then you have these conditions that when you multiply these together, this is what you do. You start with some initial value, you multiply it by the matrix, and then you go to the next step. And then when you do it, over time it gets stable. So this is a theorem, it's proved that you can quickly calculate it, right? So if you like to know what's happening. So the method we were doing here is called power iteration. And this is the same thing, I think, if, for example, I'm not sure if Google still is using this PageRank, they need to reconstruct this Markov chain every, for example, month. And then they do this matrix calculation, and then, for example, methods like MapReduce or Hadoop or these kind of things were developed because of this, because they had a huge matrix that even if you want to multiply a vector on that, you need to have some kind of distributed kind of computation. So, but this was very simple, but that's it in principle, and it worked very well in practice. So now you can think about it in any system. In many systems it becomes useless, but it's generic still. For example, if you remember this Lorentz curve practice game that we had, now I'm simulating 1000 curves. You remember these double curves, these Lorentz patterns, right? And I just take care of one dimension, right, x. And then if you generate with random initial condition, this is like 1000 patterns. So again, think about it like these random walkers, and these random walkers might be a misleading term because they are not random walkers. They might have some reason. For example, here you know that there is an underlying equation, but we call it random walkers because of the original problem. But I think it's not a proper way to call always random walkers, because these individuals, they have their own rules, but you can capture them in this setup. So I just want to show you here one case again that we have a continuous state space, so you need to discretize it in a way, and then what we do usually is that you do some kind of coarse graining. And as I told you, if you have high dimensional data, you can think about doing some kind of manifold learning and then indexing that manifold, and then take those indexes as your states, for example, right? So here, for example, what I do is that I do some kind of coarse graining. For example, I just divide them by 2 and then cast them to ints, right? So for example, I get this. If I say, like, for example, and this is number of unique, for example, states. If I divide it by 5, you understand what's happening, right? And if not, then you have this. That's it. And simply what we can do here, and because it's a kind of chaotic process, you cannot predict anything here in terms of because, for example, if you're interested to predict the pattern of one of these trajectories, we know that this is non-predictable. But what can offer Markov chain here is that you can simply make again a Markov chain on top of this sequential data. You don't care what is inside, but then you can first of all, it can tell you what is the limiting distribution. And if you remember, I think this is for x. In this case, like maybe it says that one area in this map is more likely to happen. So it's a kind of timeless picture of this dynamical system, which is somehow interesting, but it's not enough. And then what you can do else, in order to see if you can predict a single trajectory, you can start with some random numbers and move. And then this is the concept of encapsulation that I was telling you, that if you iterate now 100 steps with the Markov chain, it gives you this kind of clouds, because it doesn't predict what is the next step, but every time it says this is the chances that you go to this step and this is the chances to. So it's a kind of decision tree, but with this simple matrix calculation you just have all the combinations. And then it says, for example, when you start from here you are more likely to be here, but then gradually you see it opens up. So if you change it, so think about it as our life. And if you are a random walker, this is like, for example, if you are a random walker, this is one possible life in this state space. But the thing is that the reason I'm showing you this is that it's not like that, because, and then this is the connection to this Markov chain and Markov decision process and reinforcement learning, for example, that we will talk about it, is that now what happens that if I have a strategy in each state, for example, if I say I want to be greedy, I want to go to that state that has the higher chance, right? So this is now when you start playing in this Markov chain game, this is the definition of, in principle, Markov decision process and, for example, reinforcement learning. And then these solvers like AlphaGo or chess players, they solve it like this, but with more, not with Markov chain, but the environment is the Markov chain. So Markov chain can be used as a kind of simulator, as a kind of really like life, right? We don't know what is the purpose, but everybody is like possible from this state to go to another state, and then from there you have a lot of possibilities. And of course, if you make it greedy, I just want to show you here, but remember, we will talk about it, I think in 4 sessions, or maybe 5 sessions. We will start from this Markov decision process, and then, for example, if you take one path every time, you just say, for example, I want to take the path which has the higher probability, it creates a path. So in principle, if you have really this first order dynamical system, you can think about any of these series as like anonymized sequential data. For example, you can use this for some kind of, I would say, naive agents, for example, for drivers, for example. And for example, methods like a space syntax is here, for example. A space syntax exactly is doing that, because you have a graph, and then they say the person who is walking in the city or in the building, they take, most likely they take the path with higher chance, right? This is the case. So you can generate a lot of them and then calculate the steady state. And these are majority of space syntax measures, for example, if you know what is the space.
I would say, but they are the ones who decide which is the degree of probability based
Yes.
on the formula that they are
Exactly.
right, instead of giving the data
Exactly.
the chance of
What they
defining
do
it.
is that they really take, like, it's very similar to the graph of internet, like PageRank, that they simply take the structure of internet, and then later you have this kind of personalized PageRank that they try to keep this information that how you especially moving, so they adapt these probabilities. But the space syntax, for example, is just simply taking the structure of the street or structure of the building, for example, and then they assume that these links are important factors. And this is the so-called theory there, that they try to prove that people are taking the straight path, for example, or that right. So then you can try to prove it, but it's another story which is not, I think, interesting. So one important point that I think I already mentioned is that if you look at the problem of single trajectory, we have the problem of time series prediction. So my suggestion is that we should not use Markov chain, because in fact Markov chain is providing a very naive time series model here, where the next step is provided only based on the current state. So we will see that, for example, with recurrent neural networks or high-level, more advanced time series forecasting methods, you can do better. And actually this is becoming a topic, for example, in simulation systems, that now they take the data, a lot of data from GPS traces or mobile phone data and so on, and they literally train a very accurate time series model that predicts the movement of people, and like with this recurrent neural network, and then they put it into the simulation. So this is possible. But then what happens is that you have a kind of parametric model, because then they can train it related to the activities or important points of interest and so on. And this is I think becoming a new wave again for in terms of urban simulation, for example. So my suggestion is that it's not good for prediction of a single path, but you can do it. But on the other hand, Markov chain has a very interesting feature, a lot of interesting features, that if one is interested in the overall macroscopic properties of dynamical systems, for example, in water flow, traffic dynamic, economic networks, internet, WW, World Wide Web, and electricity network or flight dynamics, there are a lot of applications. And this is the connections that, for example, many people in control or in mechanical engineering, they are familiar with this. So there are a lot of intersection, and there are a lot of works in the field of, for example, economic networks back in 1950s, but then they are theoretical. And for example, what application that recently we did and published in this journal, +1, is exactly continuation of that one, because there was a Nobel winner, Solov. He showed that you can represent again the dynamics of flow of money between these countries based on the Markov chain. But again, he complains that unfortunately this matrix is so big, 1952, and then they're working a lot on these conditions of the Markov chain. But now we had this data, and then recently we work on that, and the results are interesting that I will show you. So if you are interested, for example, I have data, for example, for flight dynamics. Imagine you have the movement of all these airplanes all over the world, and then imagine your states are, for example, airports. I think we should have millions of airports. I don't know how many airports we have in the world, but maybe millions makes sense. So we have millions, so you have a state space on this size, and then your data is the flights, and you don't know what. And then if you think about it in terms of systemic risk, you can do a lot of analysis that I will show you. What are these analyses, for example? So what I showed you so far was the steady state probabilities, which is the most studied part, but there are a lot of interesting factors that this simple matrix has. For example, mixing times. Mixing times tells you how long does it take, for example, like here, that from here you go to the steady state. If your network is well connected, it reaches to the steady state faster. If you have disconnected areas, it's more likely that you don't get to this steady state because they get trapped in these loops, right? So these are a lot of there are a lot of interest in this kind of thing. Or there is another one, recurrence time, or there is another one, mean first passage time, that it will tell you what is the probabilistic time from any stage to another state. So these are being used in, for example, in simulator, for example, in traffic simulators, that there are publications. And Kemeny constant that I will show you in one applications. And then more interesting thing is that when you build this matrix, at the end you want to do some kind of sensitivity analysis. For example, you want to know what happens if one node is closed. For example, what happens if one road is closed. So there are lots of small manipulations. But then by studying these properties like Kemeny constants or mean first passage time and so on, you can discover this effect. So I will show you two applications that I did, and they're published already. One is I did in 2012. That time this data was very cool, that we had this data from GPS traces of like, I don't know, 20,000 cars in Beijing. So just think about it like that this is one driver, and then what we do is that we can think about it in a rational way to say, let's see what is happening here and why this driver is going there. So this is a classical simulation. They try to model these agents in a rational way, that, for example, maybe he lives here and then he works here and then he takes the shortest path and so on. Then you train a lot of these kind of assumed agents which are not existing, and then you train For example, you have a lot of agents, and then you make these multi-agent simulations, right? This is if you know, for example, MatSim or UrbanSim, they are very known applications in this field. So what we did is that we just said, let's put a grid on the city. You see these small cells, and simply say these are. We said that these are our states. So each driver is like a person who knows how to talk, for example. So he uses properly these states, right? This means that he knows where to drive, how fast it should drive, and so on. And then you have a notion of time, for example. You can say, if there's a traffic, then after 2 minutes, if you are still in the same path, so this means that there should be some traffic. If it's faster, then you're jumping in 2 minutes, you're in another step. So it's not necessarily each step to each other. Depending on your time resolution, you can make it in different qualities, right? So what we do is that now in principle we have not one of them, a lot of them, right? So you can make these kind of visualizations. So in principle you see that the traces without any information is already showing the street networks, right? Which is logical, right? So in principle what we are trying to say is that here these agents are encapsulating the traffic networks as well. The street networks. So you don't need to input this as well. Even just simple grid, and that's it. So what we did here is that we made a Markov chain on top of this. I skipped this part. And then the ideal setup would be that if you have this data, frequently you update your Markov chain. This is similar to the way Google is doing. Google is providing you services without assuming or knowing how you are doing that, but at the same time it's like that Google knows what you are doing. And here you just simply make this Markov chain, and this Markov chain gives you a lot of interesting factors, properties. For example, you can now cluster this Markov chain, and it tells you what are the emergent communities in the city. It's not related to the network, but street network has effect, but it tells you based on the movement of people, for example, in this time of the day, or this rush hour times, or weekday, or weekends, and so on, you can make the clusters of the city, clusters of the networks, right? Or for example, if you calculate this steady state probability, this tells you what are the potential traffic jams, like what are the spots with the risk of traffic jams. For example, these, and these are, data driven, right? If you don't have the data, you just need to assume how people walk and then simulate and see what are the risky areas. But here you just simply, you can say that this is the way people walk, and you don't know why. Or for example, we can calculate the highly critical areas in the traffic flows, and for example here, this is the notion of Kemeny constants. Kemeny constant is very interesting because it's a constant, but it tells you in a Markov chain the average time from any random point to any random point is fixed, and it's because of its content, and for a while nobody knew why it's constant. So the interesting point is that now we take this as a feature of connectivity. When it's very highly connected, this value is low. When it's less connected, this value is high, right? So it's a kind of average flow of money, or average flow of cars, and so on. So what we do here is that we remove one state. We just say, let's assume that you just need to close this road and see what is the Kemeny constant, and then you do some kind of sensitivity analysis. You want to know which section of the road is important. And here there was what we were interested in. I didn't know this before, but from people from traffic engineering, for example, they were interested. We have a notion of the kind of paradox which is called Barras paradox. This means that if you want to increase the flow of the traffic in a city, people usually add roads, but apparently you should close some roads, which is not logical, right? In the first hand, you just say, I add like one highway, then its flow is better. But it's being shown with a lot of cases that it gets worse because of a lot of dynamics that it will create. But here we managed to show this as well in a data-driven way, that you see this area, if you close it, and it has a kind of a spatial correlation. If you close this area, the traffic gets worse, whereas if you close these areas, for example, when it's blue, and most of them are indifferent, when you close this area, the overall flow of the city gets better. So these are the kind of questions that traffic engineers are interested to know. For example, what to do, for example, over rush hour times in different part of the city and so on. But here we simply don't care if it's traffic or flow of money or flow of water or whatever, but you can do this kind of analysis, right? And the second application that I will quickly mention to you, but if you like you can read the paper, is again similar things but in another domain, which is the domain of macroeconomic. And then we have these classical models of input-output tables, which tells you what are the connection, what are the flow of money from any industry to another industry. So this is the work of a Nobel Prize winner, Leontiev, in 1950, I guess. And this is a quite known model in economics, and it has I would say it's overexploited, right? There are a lot of works on this. But what we did is that I found this the students of this guy Leontiev. His name is Solov, as he is a Nobel winner as well. He showed that you can you can simulate this in principle, like the way Markov said about language. He said similar things for this flow of money in this economy. But as I told you, nobody used this, and then we didn't have enough data. But recently this data is available. Now we had this data for 15 years, from 1995 to 2012, and now it's updated. And simply we just create this Markov chain by that. So in principle, what's the problem is that for each year we know the flow of money from any industry within any country to another industry, including that country, all the others. So we have the connectivity and the flow rate of money from any country to another one. So this is a very schematic way that, for example, we have one node for the governments in this economy 1, and then we have one industry, and then one industry for economy 2, and then one government for that. In this case we had 40 countries or 40 economies, and then we had 35 industry within each economy. So it's a matrix of 1400 by 1400, and simply we did the same thing as I showed you before. But the difference is that every year you have one Markov chain, because here is a time varying Markov chain, because every year this matrix is not the same. So what you can do is that you can calculate all of these measures for each year, and then you can have a time series of this measure. For example, if you have a steady state of one node, which correlates somehow to the GDP of that node, or a country GDP of a country, you can study the GDP of this country over time, because you do it every year. So make it short here, I don't explain what's happening here, but what you can do in principle. This is the first result, for example, the mixing time. And we call it here as a kind of global, an index of globalization. As you see, in 1995, the value was this, let's say 280. And this 280, for example, 85, is the number of time steps that I need to reach to this steady state. For all of these matrices, I start from a random starting point and just do this power iteration, and I see when I reach to this steady state. And then in the 1995, the matrix has this value, and then you see gradually it goes down, and this is the time of financial crisis. And maybe there's a reason for that, but it was very drastic. And then you have this jump back, because this depression. This means that people are not talking to each other any longer. So it goes back. So it's simple, but somehow it's a kind of post-processing of what happened from 1995 to 2011. But it can describe you that you can say that globalization is increasing in principle. Still, I don't have data for the next, but I would say the pattern would be like this. So it means that we are getting more and more connected. And this might be a risk for the notion of systemic risk, because systemic risk is taking care of the relations. And this is the idea of this paper. And the same thing you can do with the Kemeny constants as well. You have more or less the same pattern. And then in this paper we discuss, for example, why this jump happens here, and then again it goes down. Overall, they have the same pattern, which is a good thing. But then you have this sharp edge here that we don't know why. So if you look at the steady state things, this classically this has been studied as if you are familiar with the GDP of a country. GDP is a measure of wealth, but it's independent. For example, it says how much you produce, and then it is like how much you export, how much you import, and so on. And the net value is somehow related to GDP. It's like your power. So in principle, if you produce more net production, you have higher GDP. So what we first assume is that then think about this steady state definition, that we said this is like a flow of money. So if you take a snapshot, after a while you expect how much money is within each country, right? So this in principle should correlate with the GDP, because you assume that how much share of money they have. But it's not the GDP, it's a shared GDP. So if you map the GDP of the world, this data, you can calculate it from exactly from this Markov chain or the original data. It's like that, and then of course you have this step here in 2009, but it still is growing. And this is, if you look at these countries now, this is aggregated for these countries, like you have these countries, Australia, Austria, and so on. Looks like that everybody is getting better, but simply if you look at GDP shares, the patterns are different. Now GDP share is that I just simply normalize these values, right? I just sum them and then say what is your GDP share, which is important. So then you see China is growing fast, and then countries like Germany or these developed countries are not getting higher GDP share, where the GDP share is going down. But this doesn't mean that they are not growing. They are growing, but their speed is lower than the others, and because of that their share is smaller. Because if you remember, the total GDP is increasing, right? So but this is okay so far. This has nothing to do with the Markov chain. But then we expect that if we calculate the steady state values, if you remember, now we have, like for each of these countries, we have one value for each year, and just simply map them. When you map them, you see that they have similar patterns to these GDP shares, but with a very small difference. And the difference is this: when you map them together, you have these two distinct patterns. I would say like maybe like 4 patterns. One of them, in many of them, the GDP share is higher than the steady state probability values, that we call them structural values. And then apparently they're correlating with those countries with this bankruptcy. For example, they had this financial crisis, like Greece, Cyprus, and then Spain is risky, and then Canada as well is risky. And then at the same time you have another pattern, which is those developing countries, they're going up, and then China is in a yellow part, which means that you have more structural power than what you gain still. And this ratio that, for example, in this work we are talking, is that this ratio is important. When this ratio is more than 1, which means that your steady state value is higher than 1, you're in a safe mode. And regardless of your downward or backward, for example, you look at Austria or Germany or Denmark, you see they have this blue gap, which means that they are a safe mode, but their GDP share is not growing, which is normal, right? Because they're already developed. But then you have countries like China, and then you have countries like, for example, India should be somewhere. India, which is risky comparing to China. And then, for example, Russia, or Russia is okay, but when, for example, you have, for example, Romania, that in principle they have less structural power, but still they're growing, right? So then you have countries like USA, which is losing the share, and at the same time you have this negative pattern. So if you look at this pattern, for example, this is maybe too specific if you don't know this field, but it's very interesting that this is like the countries called BRICS, like including Brazil, Russia, China, and India. And then now what we are mapping here, this is like what I told you, is this Markov chain has a lot of properties, right? Now we are analyzing these dynamical systems of world global network, economic network, but we are just playing with these factors of these matrices, right? So if we didn't have this thing, we needed to assume a lot of things about how these agents are working, what are the capacities, and so on. But for example, one application that now we can do here is that to map this ratio between these values, like this yellow, blue, and the red one. And if it's more than 1, we suggest that they're in a safe mode. But when they reach to 1, this means that they're reaching to their capacity. For example, I don't know what's the situation now, but when we were working on this, there was a discussion that, for example, China's GDP share GDP growth is going to be close to 0. And here, for example, this was the idea, but this is kind of linear system. We don't know if some non-linearity happens. Again, the system will change. But here, for example, we try to show that it looks like that they had these loops in this pattern, in 2005, and this was the time that these BRICS countries were famous, and then gradually they are getting stable. So when they go to the 1 or below 1, it doesn't mean that they're getting worse, but they have reached their limits. And this is what, for example, we claim as a kind of a structural capacity for your growth, right? So you can play with a lot of these factors. For example, now we can do a lot of sensitivity analysis with this Markov chain. For example, I can slow down the activity of these nodes and see what happens to the other nodes. And this is the notion of systemic risk, for example. For example, I reduce the activity of each node 99%, and then see what happens in terms of a steady state values to all the others, right? So if one, then we define these two notions of systemic influence and systemic, for example, fragility. Influence means that when you're when you're reducing the activities, how many other nodes get affected? So you are influencing. And then fragility means that how many times when all the other nodes are getting affected by some crisis, how many times you get affected as well. So these are different notions, right? And then you can simply do this with the same Markov chain in a careful way. It's a kind of a perturbation. And then, for example, this is the measure, I think, which is very interesting. The color and the size shows this eigencentrality or this structural power that I told you. This is the steady state share. Let's think about this, the amount of money. And then this axis shows the systemic influence, and as you can see, it doesn't correlate that much. It's correlating, but it's not 100% linear correlation with the let's say GDP and the steady state probability. And at the same time, you have systemic fragility, which is behaving independently. So these are, I mean, if you go to this field, these are the fields and these are the measures which are important. For example, if we have the flow of money, but you don't have this data. If you have a flow of money between daily transactions of banks, you can calculate some risk measures for for example, banking systems, because they're so interconnected. And before this financial crisis, nobody would look at this kind of connectivity. People would look mainly at the nodes itself. Like you say, the GDP of this country is this, so it's perfect, or GDP growth is like 10%, it's perfect, or 2% is okay because it's positive. But here we are talking at the relations, and then looking at the relations, we want to see the effects, right? And this is the last part that I will finish here. This is again similar to this Barras paradox, that here we show that if we slow down each node, what happens to the overflow of money? And then you have again this paradoxical pattern. Majority of them, the flow, I mean, you get a negative effect, like this oil industry. For example, if you close oil industry, it has a very negative effect to the whole network because the flow of money is somehow highly dependent. But then when you, for example, I don't have it here, but if you remove, for example, or slow down a lot of sectors like real estate, the flow of money gets better, for example. So, but we are not economists, and we are talking with people, for example, with economists, that they are interested to explain why this is happening. And yeah, but I think this is interesting that you have this paradoxical effect. So think about it. I mean, if you're interested, for example, in this field like budgeting or like countries, national plans, and so on, they're always thinking about this. What would be the gain of each of these nodes? How we should allocate our budgets to these kind of things. So these are all applications. Or if you are thinking about the water pipeline network, again, you have this problem. If for example, you have a broken pipe somewhere, which area is the most risky, right? You have again a network and you want to know where you should care more. So all of them, you have this generic notion of dynamics of some flow of something, but you don't want to start with the rules because you don't know the rules. So it's kind of data driven, and this Markov chain can easily help you, for example, for many applications. So this was, mainly this for today. I think it's enough. It was a bit longer than 1 hour that I told you. So yeah, then we have a lot of extensions. As I told you, we have time varying or inhomogeneous transition matrices. We have continuous time, status space variation, yeah, status space exploration, and then you have the notions of hidden Markov chains that I didn't talk at all. There's another thing. And then you have this notion of random fields. Again, they're very interesting topics, but it's not good for now. It's again different topics. And they have a lot of use, for example, in image processing, which has nothing to do in principle with, for example, with this kind of dynamical systems. But I want to show you that this method is very generic, and if you get it, it will be like a kind of pairs of glasses that you, by that you can look in different fields around it. So there are other topics that I just touched, for example, this Markov decision process and reinforcement learning, and then you have this relationship between Markov chain in terms of memory to recurrent neural networks, that we will talk about it later, and hidden Markov chain, and then Markov chain Monte Carlo. And then, for example, there are interesting topics, philosophical discussions, and for example, this is, I like it, is a talk about this, why time is a one-dimensional arrow. So the idea is that you can think about life or time as a kind of, there's a concept of a Boltzmann machine, or Boltzmann box, I guess. If you watch this presentation by Leonard Susskind, he is a physical physicist and theoretical physicist. So this is very interesting, but then you can explain why time is a one-dimensional arrow by this notion of Markov chain as well, which is cool. So that was it mainly. I hope it was interesting for you and you find somewhere other applications. Next week I will focus again on Markov chain, but in the beginning, and then think about Markov chain as a kind of data-driven representation, and then from that point we go to quickly to this recent successful application in natural language processing. I hope I'm trying to repeat a lot of time, and I'm trying to relax these assumptions of applications, and this is what I promised in the first day, that these applications become arbitrary in these fields like economy. Of course, you need to know a lot about it if you want to contribute, but when you get these kind of abstract tools, and with enough data, in principle, you can go everywhere. So it gives you some kind of new freedom, I would say. So if I show you a lot of application, it might be boring, because if you, for example, say, okay, I don't have an interest in that, but at the same time you can think about these methods, that how generic they are. And for example, because of that, these computer science companies, they will go to any field soon if you don't learn these techniques, for example. Well, okay, that is from my side. If you have any questions or comments. And if not, then see you next week.